这些个自由化、可视化作业。
对。我本来今天想去健身。我说我本来今天想去健身的，然后。
每天下课完要去健身。
你每天下哪节课？
就这节课一下课就是这个。
你东西都在车里是吗？
对啊。
我本来想今天早上开车去，早上车位应该比较多。
除非很早。有人。
有吗？好，我这不行。没有，我还。不过你看到就好。
对，好像动了，它延迟好高啊，延迟10秒吧。还好那个作业找到答案。几级吗？
是 ID 那个 IDE 是啥呀？你们哦，你们已经到什么 project 了？
没有。IDE 是什么？
就是这个编辑，后面你用那个编辑的东西。
这个吗？
哦，这是 JavaScript 是吧？
对。我 Java 终于给学透了。
你挺快的，才几个礼拜。放心，用电脑开启。
你有没有买比特币？你有没有买比特币？
没有，我有美国股票，但是我最近17000块钱股票掉了1.9块钱，就是2000。
我15000掉到5000左右。
你是比特币吗？
就虚拟货币。
我没有买，我又买了股票。
之前赚了一点，后来不知道咋回事就掉下来了。现
在
我
你知道你买的是哪种吗？
啊？
你知道你买的哪种？
不知道。我买的爱达龙和以太坊，还有 EOS， 乱七八糟。
啊，后面2个我听过，第一个我没有听过。股票大跌。
股票这两天在跌，好像。这两天是不是在跌一直？
你说股票？
你买的是什么股票？阿里巴巴吗？
不是美国的。
是什么公司？
就是科技股。
就是大股牌小公司。是什么公司？
就是谷歌、iPhone、Amazon 乱七八糟，这个科技股。
哇 ，Amazon 这个
咱俩好像在直播咱们的谈话。关了。啊，不好意思。
好多人没来啊。
是不是有什么别的课？期中考试的？有可能。
不要期中考试的课。
不，就是有别的课在期中考试，所以他们就不上。
那个韩国人是学霸，
韩国人他们是中国人。
他是学霸。你做这样，你做这边吧，
那边。
你做这个。
Okay. Okay, we should start. So, in the last lecture, we have finished the topic about regression, and we introduced general linear regression with multiple explanatory variables. We also introduced the simplest nonlinear regression model, which can be considered as a natural generalization of linear regression, that is called polynomial regression. So, as later in your later investigation in data science, so machine learning, you will get to know a lot of different regression models as well as classification models, and different models actually have a different regression function or classification function. And if we want to estimate the model parameters from a set of training instances, we actually need to write down some objective function. So what kind of objective function we have used in fitting the regression models? Whatever, linear or polynomial regression. That's the two models we have discussed so far, right? So what kind of objective function we used? SC. Yeah, SC, right? So so let us write down a general form. Right? So given the set of explanatory variables. So here x, I assume it is a vector. Right? So to emphasize this point, I put an arrow on top of it. So it's a vector. It may consist like d explanatory variables, and I want to use these d explanatory variables to predict our target variable y, which is also referred to as the dependent variable. Right? And then we may choose some regression models, say linear regression or nonlinear regression model. So now forget about the detailed form of the regression function. We just assume the regression function has is a function of the explanatory variables x, and it is parameterized by some parameters alpha. So alpha could be a vector as well. So you can make the correspondence to different regression models. Like linear regression, alpha will correspond to the regression weights. And if we are doing polynomial regression, the alpha corresponds to the coefficients for different polynomial terms in our regression functions, right? So anyway, to specify a particular regression function, we need to identify the appropriate setting of those parameters. Right? Then a natural question would be, how can we find out the appropriate setting of the parameters? This process is referred to as training or learning procedure. So what is the training and learning procedure? We assume we're given a set of training instances, meaning that we have n pairs of input values and output values, right? So we can denote it by x1, y1, x2, y2, continue until xn, yn. And we assume these are our observed instances of the explanatory variable values and dependent variable values. And want to fit our regression model, which is expressed by this parameterized function, to this n training instance pairs. Right? So what's the fitting procedure? In our previous lectures, we actually write down an objective function. We call it SSE, right? Sum of the square error, which is the summation over some squares, summation of the square error of using our regression model to predict the target variable values. So it is yi minus our prediction. This is xi, and take square. And then to find out the best parameters alpha is now equivalent to minimizing the objective function SSE. Right? And in our particular case, namely the linear regression model and polynomial regression model, we can show that this minimization will end up with an analytical solution of the optimal alpha. But in many cases, actually in most of the cases, when we choose a more complex models, not linear regression, not polynomial regression, you usually cannot solve the gradient being 0. It's really not analytical. Then in this kind of case, in this kind of situations, which is actually the 99% cases in practice, how can we estimate the best parameters alpha? How can we do that? In other words, how can we minimize our objective function, SSE, with respect to the parameters alpha? So remember, this SSE is essentially a function of alpha, right? So here the training instances yi and xi, x1, y1, x2, y2 to xn, yn are given fixed, right? And when we want to minimize SSE, actually we want to minimize it with respect to alpha. So SSE is essentially a function of our parameters alpha. So it's actually an objective function alpha. And we want to find out the optimal alpha that make the value of SSE to be the smallest. And this is our goal. So, and in most of the cases, we cannot derive the optimal values of alpha. Then how can we find out the optimal value of alpha? Obviously, we cannot depend on some specific mathematical formula. We need to come out some algorithm. So this kind of algorithm is usually called optimization. So maybe some of you have heard about it. It's kind of a big branch in the computational, in applied mathematics. It's called optimization. So today we're gonna enter into another topic in optimization. So we'll give a general strategy to maximize or minimize some particular function. And this strategy is called gradient descent. So gradient descent may be perhaps is the simplest optimization algorithm or framework, but at the same time, the most widely used and most useful algorithm to minimize some particular objective function or maximize some particular function. With that being said, in the future exploration in data science or machine learning, whenever you can come out an objective function, for example, SSE, and when you want to estimate the model parameters, you can use a gradient descent strategy to develop their own estimation algorithm. And the estimation algorithm is to look for some best model parameters whose objective function value is minimum or maximum. So remember, SSE is just one objective function. So in practical applications, you can choose different types of objective functions. For example, in our review of the probability theory, we actually mentioned another type of objective function. What is that objective function?
Maximize the likelihood.
Yeah, the likelihood function. Right? So the likelihood describes the probability that given some parameters of the probability model, how is likely the observed data samples are sampled, right? So obviously, if we want to find out the optimal model parameters that determine the probability model, we need to maximize the likelihood. Right? This is a very common used procedure, and in that case, our objective function becomes a likelihood function of the model parameters. And here in our linear regression case, of course, we choose to use the SSE, right? We minimize SSE. But in whatever case, the general procedure is as follows. Right? We first build up a model, a machine learning model or data science model, whatever thing, right? The model describes how you make the assumption of your prediction function. In the continuous case, it is a regression function. In the classification case, it is a classification function, right? And then you come up an objective function that integrates your prediction model to predict our observed values in the training data. So the modeling procedure will ask you to provide an objective function. And then in the training procedure, we're actually trying to either maximizing your objective function or minimizing your objective function and find out the optimal values of the model parameters. So basically all kinds of machine learning or data mining tasks consist of these two steps. So this is a very general description. So suppose now we have known how to formulate our model and formulate our objective function. So the remaining task is to minimize or maximize this function. And as we just mentioned, in most of cases, you won't have some analytical solution of the optimal values. You have to optimize it using some algorithm. That's why, since today, we're going to introduce a very commonly used strategy called gradient descent. So before we talk about the details of gradient descent, I would like to introduce several commonly used concepts in the general optimization area. So from now on, I use the function f. I use f to denote our target function or objective function, and we assume our input is a vector. Of course, you can. The scalar is a special case of vector. Right? So we just generally assume it is a vector, and this function is a mapping between a d-dimensional space, input space, to the real value. And our task is to find out some general strategy to minimize this function with respect to the input alpha. So namely, we want to find out the best alpha star that minimize this function value or maximize this function value. So let us first introduce the concept called neighborhood. So given a particular value of alpha, we denote it by alpha 0. And here, to emphasize it could be a vector, I always put an arrow on top of this vector, So given a particular point in a d-dimensional space, denoted by alpha 0, we can define a neighborhood of alpha 0 specified by some radius r. So here the subscript r indicates the radius. So what's the neighborhood of alpha 0? Geometrically speaking, you can consider it to be a ball or a sphere. Right? The center of this ball is alpha 0. And all the points inside this ball and on the surface of this ball consist of this neighborhood. This is the definition of the neighborhood. And to define neighborhood, you need to designate a.
Is it a closer?
Yeah, neighborhood is usually assumed to be a closed set. Yeah, it's not open set. Yeah. So that's why I said the surface of the ball is also included in the neighborhood. So any other questions regarding this definition? Okay, good. So this is an intuitive explanation of this concept, right? So here we give a more rigorous definition. It's actually a set, right? A set of d-dimensional points, such that the Euclidean norm between each point and the alpha 0 is less than or equal to our specified radius r. So this is the definition of the neighborhood of alpha 0 given the radius r. So this is the Euclidean norm. The Euclidean norm means the distance, right? The distance, the Euclidean norm of two vectors indicates their distance in the Euclidean space. If you still have an impression about what we have discussed previously, right? In the vector, about linear algebra, right? So basically, it says this is alpha 0, right, in the d-dimensional space, and this is some arbitrary point like p, right? And what's the distance between p and alpha 0? It is the Euclidean norm of the difference between p and alpha 0. And if it sounds strange to you, like you can check out the materials we have discussed previously and use the definition. You'll find it is exactly the Euclidean norm. So this is a definition of the neighborhood. So given the definition about neighborhood, we can define several particularly important points in the function. So first type of point, input point in function, is called local maximum. So what is local maximum? Any intuitive guess? Largest distance.
The origin of the ball.
No, actually. Yeah, can anyone provide other?
The largest p in the neighborhood. Largest p value.
No, yeah, its definition has something to do with the neighborhood, but you can consider it more toward the characteristics of a function, right? So remember, in our learning procedure, our training procedure, we're trying to find out some maximum value of the function, right? So this is directly related to the local maximum.
P is great. Oh.
Yeah, you can imagine, right? Let me write down. Let me draw a function. This is in a one-dimensional space. So what is local maximum? Yeah, that's a way to find out. That's properties of maximums. So basically, so what is maximum? Maximum is the places here and here, meaning that in some local region of the function, the value of the function at maximum are bigger than any other function values. That's the local maximum. It's just as the name suggested. So let me give you a rigorous definition. Or before that, we can also look at what is local minimum. Right? So what is local minimum?
The lowest points.
Yeah, the lowest point. Right? So local maximum, the highest point, but not exactly rigorously the highest point. Right? Among all the highest point, the most highest points will be the global maximum. Right? So local maximum means okay, inside some local region it is the highest point. And similarly, local minimum means that okay, inside some local region it is the lowest. So now let us give a rigorous definition of the maximum. We say alpha is a local maximum if there exists some radius such that for any point inside the neighborhood of alpha with radius r, its function value is smaller than or equal to the function value of alpha. So this is the definition of local maximum. So as we just mentioned, right? So we said that in some local region, the function value is the maximum. Right? So what is the local region right now in the definition? It is the neighborhood, right? So we can look at the curve here. So actually we can find out a local region. You can just draw a circle right, around here. Right? We know that for any function input inside the circle, the function value must be less than or equal to the function value at this point. Right? That's why this point can be considered as a local maximum, because it's locally maximum function values. And similarly, for this local maximum, if we draw a neighborhood, right? If we draw a neighborhood, I know that okay, for any input inside this neighborhood of this input of this local maximum, the function value is smaller. But it's just the local region, right? Particularly for this local maximum, if we enlarge the neighborhood, say enlarge the neighborhood to include this region, right? Then we know that the input at here, its function value is bigger than here. So that means inside this region, although it's also a local region, this the function value here is not maximum. But it doesn't matter. Local maximum only requires to find one neighborhood, no matter how small it is, as long as there's one neighborhood, such that the function value is the maximum. Then it is local maximum. And correspondingly, now that there is a local maximum, we also have a global maximum, right? So what's the definition for global maximum? Can you give some introduction on that?
The largest value of the function.
Yeah, the largest value of the function. Yeah. So here we do not need to specify any neighborhood, right? We do not need to specify any local region. We just, if we say alpha, okay, is a global maximum, that means for any input in our domain, that is the d-dimensional space, we have the function value to be less than or equal to the function value of alpha. This is a global maximum. So if we're trying to maximize this function, right? So obviously the best point would be the global maximum. But unfortunately, in most of our cases, we cannot guarantee we will be able to find out the global maximum. We're at most to identify some local maximum. The reason is because the function is really highly nonlinear, non-convex, and you even are not sure how many local maximum do they have. They might have an infinite number of local maximum, and you don't know where is the location of the global maximum. So in most cases, this is kind of a trade-off. This trade-off between your expectation and the practice. Right? So usually we end up with some local maximum. That's fine. That's why we like to introduce local maximum first, and then go to the global maximum. But for a particular type of function, namely convex function, we will introduce it later. The global maximum overlaps with local maximum. So convex function has a very good property. So this is the definition of global maximum, local maximum. So the question, there's a question. Is global maximum a local maximum?
Yes.
Yes, right? Because for global maximum, any input inside the whole domain, the function value is smaller than. Then you can draw any local region. You can draw any neighborhood. You can guarantee that all the input in this neighborhood, their corresponding function value is smaller than f alpha, right? So we can introduce some variance for the maximum and global maximum. For example, if we erase the equality here, so let me preserve use a blue marker. So if I erase the equality here, and also erase the equality here, and also, of course, I need to ensure that any point other than alpha, right? Otherwise they are the same. Right? Here, any point other than alpha. Then, if some point alpha satisfies those properties, but with a strict less than, then it is called a strict local maximum or global maximum. So this is kind of a variant, a definition variant. Right? We simply remove the equality here. So we require any inputs in a neighborhood whose function value is strictly less than f alpha. Then alpha is called strict local maximum. And similarly, we can define a strict global maximum. So obviously, we can use the same language to define local minimum and global minimum. And the global minimum. So we can just copy the definition here, right? You just change the direction of the equality, right? From less than or equal to be bigger than or equal to. Right? Also, you just change the direction of equality in the definition of global maximum you end up with the global minimum. So I won't copy those texts again. So in our lecture, we'll assume the target function f, the objective function f, has nice properties, meaning that they are differentiable. So we know that we can calculate the gradient of alpha, meaning that there's no meaning that in the whole domain, at any input, it has valid gradient. And then you can prove that a local maximum or local minimum has a zero gradient. So let me explicitly write it down. So if alpha is a local maximum or minimum, and f is differentiable, differentiable, you can prove that the gradient at alpha is zero. I won't show you how to prove that. It's actually the content we have covered in the calculus course. So if you're interested, you can try to prove that after the class. It's a good review of our calculus course. Okay. So then knowing this property give us some guidance in practice. As we just mentioned, in many learning or training procedure, we are either maximizing our target function or minimizing target function. And how can we ensure our function has reached some maximum values? How can we do that? Yeah, this is one way, right? That's obviously one way. Right? But according to what we have discussed just a minute ago, right? We know that if some input is a local maximum minimum, its gradient must be zero, right? And then to check whether we have find out a alpha that makes the function value to be a maximum or to be the biggest or smallest, we just check the gradient. Right? If the gradient is zero, then maybe we have arrived some local maximum or local minimum. And this is a very commonly used trick. But be careful about this trick, because this is just a sufficient condition. It's not a necessary condition. It means that if some point, some input alpha 0, which is inside our domain of the function, and we also have the gradient at this input alpha 0 is 0, we cannot conclude that alpha 0 is 100% sure a local maximum or minimum. There's no 100% guarantee. Although in many practical cases, we simply use this sufficient condition to check whether we have arrived at some local maximum minimum. But it does not mean that if you really have a zero gradient, we can truly guarantee your point you now arrive at is a local minimum or a global minimum. So then what if alpha 0, who has the zero gradient, is neither a local maximum nor a local minimum? Then what does this alpha 0 mean?
Saddle point.
Yeah, I heard. Right. So if alpha 0 is not a local maximum, global maximum, alpha 0 is called a saddle point. So actually, our optimization procedure in the machine learning and data science, the saddle point is where we're trying to avoid, try our best to avoid, because it's actually not local not maximum or minimum. So here I can give you the intuitive example of saddle point. So let me draw a function. So in one-dimensional space, suppose I have a function like this. And here alpha 0 is a saddle point. Why? Because if you check its gradient, this gradient is the slope of the tangent line at the point, right? And this slope is 0, meaning that the gradient is 0. But this is not a local minimum, not a local maximum, because there's some part of the point on the left-hand side is smaller than it, and some point of right-hand side this function value is bigger than that. Right? And I can also give you a two-dimensional space. So suppose we are in a two-dimensional space such that our input consists of two variables, x1 and x2, and this is our function. So you can draw a function. So in a two-dimensional space, the function curve is not a single curve; it actually becomes a surface. So let me draw a surface like this. So this surface looks like a harness. Right? Looks like a harness. And then you can take a look at point here. This is a typical saddle point. Why? Because from one direction of this function surface, you will find this is actually a local minimum. So which direction?
The x2 direction.
Yes, parallel to x, right? Parallel to x-axis. If you follow the direction here, we find, okay, the saddle point is the local minimum. But if we look at function direction in orthogonal direction, right? Follow it from here. So now this point becomes a local maximum. But overall, this point is neither a local maximum nor a local minimum. And you can check that the gradient at this surface, the gradient of this point at this surface is also 0. So this is a typical example of the saddle point. So actually, in most of cases, the local maximums, global maximum, and saddle points are minority points in function. The most functions, the most input in the function are not any of the three types of points. And we call this kind of point as regular points. For example, all the input here are all called regular points. But we're mainly interested in how to move from some regular points to our desired points, like local maximum or local minimum. But we should be aware that there is no guarantee that all functions have some saddle point or maximums or minimums. For example, if the function is unbounded, a typical example is a linear function. It's a line. So you can see in this function there's no local minimum, local maximum, no local maximum, no set of point. But if the function looks like this, it's a horizontal line, then what will happen?
All points are maximum and minimums.
All points are maximum and minimums. All points are global maximum and global minimums. Okay, any questions so far? Oh, good. This is several very commonly used concepts regarding optimization, because in the future, you might not only investigate gradient descent, you might investigate like quadratic gradient descent, like Gaussian-Newton methods, those kind of more complex optimization algorithms. But they are all defined based on those important concepts. So you should be familiar with those concepts, and don't be confused. And next, we will introduce a particular type of function called convex function. As we previously mentioned, this is a very important type of function and has many cool properties. So to introduce the concept of convex function, we need to first know the concept called convex combination. So we still assume our function input is in a d-dimensional space. So consider 2 points in a d-dimensional space, 2 inputs in a d-dimensional space. Say alpha 1, say alpha 1, and alpha 2. And now we introduce a scalar between 0 and 1. We denote it by lambda between 0 and 1. Then we can use lambda alpha 1, alpha 2 to composite a new point in the d-dimensional space, which is simply lambda multiplied with alpha 1 plus 1 minus lambda alpha 2. And that's denoted by p. So we can say this is actually a combination of alpha 1 and alpha 2, right, with the coefficient lambda. And it will end up with another point in the d-dimensional space. And this combination is called a convex combination. So basically, what is convex combination? A linear combination of 2 vectors. And also, we need to ensure that the coefficient in the linear combination must be between 0 and 1. This is called convex combination. And geometrically speaking, where is the position of the combination? P. Right. So suppose this is the position of alpha 1. Right? This is the position of alpha 2. Right? So where does P locate? Where does P locate? Actually, P locates on a segment that connects alpha 1 and alpha 2. It should be here. So if you set lambda to be 1, then where is P? Yeah, then P moves to alpha 1, right? If you set lambda to be 0, then P moves to alpha 2. Right? Of course, if you set non-zero, this is strictly between 0 and 1, then P stays strictly on this segment. Any questions so far?
What is it being divided by?
What?
What is P being divided by? To the right of that.
Here?
Yeah.
This is a combination of alpha 1, alpha 2, right? Two vectors, alpha 1, alpha 2, which is lambda multiplied with alpha 1 plus 1 minus lambda multiplied with alpha 2, right? It's just the linear combination of alpha 1, alpha 2.
But what is it being divided by?
Convex combination.
Okay.
This is a combination, right? This is a combination of two vectors. So we call this particular type of combination convex combination. Or is this is my writing of the English words to
It's just confused by like it looks a little bit like a fraction,
Yeah.
but that's it.
like fraction?
Like a fraction, like the whole thing.
Oh,
Yeah.
okay. This is called convex combination. Right? So now, given the concept of convex combination, we can say that all the convex combinations between 2 points, alpha 1, alpha 2, actually form the segment which connects alpha 1, alpha 2, right? And then we define step 1. Step 2, we define the convex set. Because if we define a convex function, the domain of the function must be a convex set. So what is convex set? So first, it is a set, right? A set of so we say S is a convex set if for any two distinct points, alpha 1, alpha 2 belongs to S, the convex combination of alpha 1, alpha 2 belongs to S as well. So basically, it is closed under the operation of convex combination. This is called convex set. So to give a intuitive example, so suppose we're in a two-dimensional input space, right? I can draw a circle, and this circle is a convex set. Why? Why? We can check according to the definition, right? So if a set S, so here is the circle, right? If the set S is convex, meaning that any two distinct points, their convex combinations all belong to S, right? So we can just pick up arbitrary 2 points inside the circle, right? And what are their convex combinations?
Points on the line segment between the two.
Yeah, exactly, right? As we just mentioned, right? The convex combination of two distant points form a segment which connects the 2 points, right? That will be this segment. That will be this segment. And then we say this segment belongs to this content is this circle, right? Actually, you can test it with arbitrary 2 different points. No matter if you are on the surface of the circle or inside the circle, no matter, right? You can join. You can connect them by segment. You will find that the segment is exactly inside the circle. You can try. You can try here, here, here. So a circle in the two-dimensional space is obviously a convex set, right? And then we can generalize to like a d-dimensional space that will correspond to a ball, right? A sphere. And you can imagine that a sphere in the 3-dimensional space and 4-dimensional space are convex as well, because if you connect any 2 points inside the ball, the line segment must be contained in the ball, right? This is one example, but let me give another example of non-convex set. For example, I draw a heart. In a 2-dimensional space. Is this a part a convex set? An idea?
No, because if we pick the top two top point on the third and connect it, the line is not in the heart shape.
Yeah, exactly, right? We can also check the convexity according to the definition. We pick up 2 points, right? Here and here. And we want to check whether the segment between the 2 points are all included in the heart, right? It turns out no, because when we draw them, we know part of the segment here, right, is outside the heart. That means this subset of convex combinations are not included. Then this part is not convex set.
Is the line segment also a convex set? Like, the convex combinations of 2 points form a convex set? So, like, that line segment, like, yes, that, as long as the endpoints are included.
Yeah, that's a very good question. So what's your answer?
Yes.
Yeah, the answer is yes, right?
Yeah.
So you can imagine, you can start with, that's the way how to construct a convex set, right? You can start with 2 points, right? And then how can I construct a, say, a smallest convex set that contain the 2 points? How can we do that? We just add that segment into that set, right? And then we can show that, okay, any 2 points inside this line segment, their convex combination is inside set. It is self-contained. Any questions so far? Okay, great. So now we can define our convex function. So we define our convex function f, which is from a mapping from a convex set. Of course, this convex set, we can assume it is a subset of d-dimensional space, as long as it's convex. Right? Map from a convex set to a real value. And we require that any two inputs in our domain, 2 distinct inputs in our domain, their convex combination, meaning that there exists a alpha, the lambda, which belongs to 0 and 1, such that the function value of their convex combinations, which is a function valued at lambda of 1 plus, so let me add the arrow to emphasize it could be vectors, must be smaller than or equal to the convex combination of their corresponding function values. That means alpha times the function value at alpha 1 plus 1 minus lambda times the function value of alpha 2. If for any 2 inputs in the domain, this property satisfies, and any, of course, for any lambda, this property is satisfied, then we call the function f is a convex function. And this inequality is usually referred to as a convex inequality. So we can take a look at the some intuitive example about convex function. If we just throw out the definition, it sounds a little weird. So we can look at a quadratic function. Here, this quadratic function. We can check whether this function is convex or not. So first, the quadratic function, the domain is in the full R2 space, 2-dimensional space. The full 2-dimensional space is obviously convex. So the domain is convex, no problem. Right? And then we need to check whether it satisfies this convex inequalities for arbitrary two inputs and arbitrary lambda. Right? So let us pick up 2 points, right? So we denote here as alpha 1, and we denote here alpha 2. So this is 2 inputs, and this is the x-axis. Sorry, I should draw a perpendicular line. So this is alpha 2, this is alpha 1. And now, if we pick up some lambda between 0 and 1, then where is the location of the convex combination for alpha 1 and alpha 2?
So domain should be R1.
Oh yeah, domain R1. Yes, you are right. Because we're only looking at the a scalar function. So now, if we pick up some coefficient lambda between 0 and 1, then where is the convex combination between alpha 1 for alpha 1 and alpha 2? Yeah, it must be inside the segment, right, which connects alpha 1 and alpha 2. So that's denoted here to be here, right? Alpha bar to be lambda alpha 1 plus 1 minus lambda alpha 2. And then, what's the function value of the convex combination? It is here, right? So this is the function value of the convex combination. And then we can compare it with the convex combination on the function values. So what's the convex combination on the function values? So we know the function value at alpha 1 is f alpha 1, right? The function value at alpha 2 is f alpha 2, right? Then we're gonna do the convex combination of these 2 values. And how can we find out its position in this curve? Yes. Let us review our high school maths, right? Geometry, right? So we just connect. So this is a 2 perpendicular line, right? And we just need to connect this point and this point. And their convex combination, that means the alpha 1 lambda times f alpha 1 plus 1 minus lambda f alpha 2 will simply be what? I draw at the same position, right? I draw a line and cross here and find out the cross point here. So this would be the convex combination of the function values. Any question at this point? That's just some geometric way to find out the convex combination. It's very straightforward. And now we can to compare which value is better, right? The convex combination of function value itself or the function of the convex combination of the inputs. We just compare the location of the 2 points. Right? Obviously, the convex combination of function values is bigger, right? Because it is higher than the point at the function curve. That means this inequality holds. So actually, this conclusion holds for arbitrary 2 points on this quadratic curve, this quadratic function. You can try it. For example, this is a function, right? And you can try 1 alpha here and alpha here, right? and the convex combination of the function value will be here. And then what is the function value of the convex combination? It's here. So this function value of the convex combination is much smaller than the combination of function values. And you can draw your own lines and then do the comparison on this curve after the class. You find they always hold. So later, actually, you can prove that the function of the quadratic function is actually a convex function. We can give a very rigorous proof. So, any question in understanding this concept? Okay, good. So there are many good properties of convex functions, but the most important property is that if a convex function has a local minimum, then it is the global minimum. That means the local minimum of a convex function overlaps with the global minimum. And remember, in general, there could be many global minimums in a function, right? So if I draw a function like this, a wavy function, there could be a lot of local minimums, right? But if your function is convex, you will only have one local minimum, which corresponds to one global minimum. So this is a nice property of the convex function, because once we have identified a local minimum, bingo, we get the global minimum. And also, due to the uniqueness of the local minimum and global minimum, we can prove many nice properties. That's why before the rising of the deep neural nets, people in machine learning research always try to formulate a training objective function as a convex function. Not only because of the computation issues, but also because of uniqueness of the convex function that can help you to give a lot of fancy properties. But right now, the real world is complex. It turns out to be complex. People found that, okay, if my objective function is highly non-convex, although every time I can only guarantee a local maximum or local minimum, but as long as you have enough large data, it turns out it can be much better than your convex objective function. So that's the reality. So we have introduced these basic concepts of different types of functions. So now we begin to talk about the strategy to minimize or maximize a function. And here we only focus on minimizing a function. Why? Because maximizing a function is equivalent to minimizing the minors of that function. So the technique, the way to maximizing a function is totally equivalent to minimizing a function. So for convenience, we only focus on developing algorithm to minimize a function. So the question would be, how to minimize a function? Use a general strategy, general process. For example, if I start, so this is a function, right? This function. I don't know where this function is. If I start with some point, say alpha 0, can we have a general step to move the input location toward the location that the function has a local maximum status? If there is such kind of strategy, how can we implement that strategy? What kind of information we should use? An idea? the most naive way is to, okay, I just, for example, surrounding alpha 0, I just random pick up a bunch of locations and then examine the function values, right? If I found, okay, for example, I random pick up a position, 2 positions here, and then evaluate the function values. I found, okay, at this position, the function value gets increased, right? Then I move alpha 0 toward this direction, toward this input. Otherwise, I move toward the other, right? This is one way, but obviously this is very inefficient because I don't know whether my my random guess will lead me to the optimizing direction, right? I could waste a lot of resources in evaluating the function values at different locations. Is there any better way to find a direction that decreases the function values? Any idea?
If given any point, we always see that the slope is, if the slope is positive, then we know the higher side is at the right side. If the slope is negative, then we know the higher direction is at the left side. So it might be useless. Maybe we can use the slope.
Okay, right. So what's the meaning of slope?
It's the direction.
The increase on the y direction, on the unit x direction.
Yeah, I know. So you should give a professional name of the slope. What does slope mean?
Gradient.
Yeah, gradient, right? This is something we have spent quite a long time in calculating, right? This kind of headache and annoying calculation. But this is very useful because the gradient contains important information to indicate a decreasing or increasing direction for functions. So we can start with an intuitive example, and then we'll give a rigorous analysis why the gradient can indicate the changes of the function values. So imagine our function curve is like this, right? And of course, this is a one-dimensional function, right? This is x. So we start from here, alpha 0. Now I want to, here is not good. So let me assume we start here. This is alpha 0. Now I want to move our input location towards some direction to decrease the function value. And what kind of direction we can choose? If we look into the gradient at alpha 0, what's the gradient of alpha 0? Geometrically speaking, is actually the slope of the tangent line of the function curve, right? And the gradient is actually the slope of this tangent line. And we know this slope is positive. The slope must be positive because this is tangent line. If the tangent line is like this, then the slope is negative. Now, if we move our input location toward the direction of the slope, because slope is positive, meaning that the gradient is positive, it means that we should move alpha 0 toward the right direction of x. Right? It is increasing the location. And what can we observe? If we move alpha 0 here to like alpha 1 here, what's the change of function values? Increasing, right? And move alpha 0 to alpha 1 actually is to increase the input location, which is consistent with the direction of the gradient, because the gradient is positive. So now, here we can say, if we move the input toward the direction of gradient, we actually increase the function. And someone may question this point. Let us look at another example, right? Say now my function is here. It looks like this. Suppose my function now is not monotonically increasing, right? It's kind of decreasing. So now I start from here, alpha 0. And again, we want to move the input toward the direction of the gradient. So now, how about the direction of the gradient? This is the slope of the tangent line, right? But this time, the tangent line has a negative slope, meaning that the gradient is less than 0. The gradient is less than 0. So if we move alpha 0 toward the direction of gradient, meaning that we move in the opposite direction of x-axis, right? So now that means we should move alpha 0 along this direction. Say here we'll end up with alpha 1, and what can we observe? What's the change of function value? The function value still is increased, right? So by these two analyses, we can see that intuitively, when we move the input toward the gradient direction indicated by gradient, we actually increase the function. Now, if we want to minimize function, what should we do? Any idea? Yeah, I'm showing that, right? If we move the input toward the direction, which is consistent with the direction of the gradient, we actually increase in function. And now, if we want to decrease function, how should we move the input location? Yeah, the opposite direction of the gradient, right? We just move toward the opposite direction of the gradient. We're decreasing the function. That's why it is called a gradient descent. Because we move toward the negative, the totally opposite direction for the gradient, we're actually decreasing the function. And we will continuously decrease function, we'll end up with some local minimum. That's the idea. So now, let us review the basic concept of gradient, and then maybe we don't have time to give a rigorous proof why gradient can indicate the direction to increase the function. So we can look at the definition of gradient first. So how can we calculate a function, its gradient, with respect to its input? If alpha, the input alpha is d-dimensional input vector, right? The gradient must be a d-dimensional input, d-dimensional vector. Then what about each element in this gradient? What about each element in this gradient? What is the first element in this gradient vector? So assume each element in our input is alpha 1, alpha 2 to alpha d, right? So first we should be clear that the gradient of function with respect to alpha is also a d-dimensional vector. And each element will be the partial derivative of the function over the element of the input, right? So the first will be a partial derivative of f with respect to alpha 1. And second would be a partial derivative of f with respect to alpha 2 and continue. And last will be partial derivative of f with respect to alpha d. So let us make a final practice to review how to calculate gradient. So suppose alpha is three-dimensional. So the three elements are x, y, and z, and our function will be 3x squared minus 2y cubic minus 2x e to the z. So what's the gradient of f or alpha? So the first element will be the partial derivative of f over x. Right? The second is partial derivative of f over y, and third partial derivative over z. And how can I compute the partial derivative of f with respect to x? What is this? We just treat y and z as a constant, right? Because they have nothing to do with x. And then we take gradient with respect to x only. So the first term, the gradient with respect to x will be 6x, right? And second term is constant to x. So you can just skip it. And third term, what's the gradient of x? Minus 2 e to the z, right? Because e to the z are constant. And similarly, we can calculate the partial derivative of f with respect to y, right? So the first term, which only contains x squared, is constant to y. So we only have a second term, which is minus 6y squared, right? And third term does not contain y, so it is constant to y as well. And the partial derivative with respect to z, you can see the first two terms are constant to z, right? Only on the last term. And derivative of e to the z is e to the z itself. So it is simply minus 2x e to the z. Now we end up with the gradient vector for the function f. And then if you are given any specific value of x and y and z, say to be 3 minus 2, 1, then we can evaluate the three partial derivatives at the three values. We end up with our gradient vector at some specific location. Here, right? Any questions so far? Okay, yeah, let us stop here today. And the next class will explain why the gradient direction is a very good direction to